So originally, the datagram switching was what was employed over the packet switching core. This was in 1970s, but in late 1980s and early 1990s, it was felt that the packet switching, the datagram switching over packet switching cannot support real-time applications like audio or video because these applications have delay constraints. By which I mean a packet has to reach the destination before some designated time. And if there are many packets ahead in the queue at a switch, this packet, the real-time packet, can get delayed. So this is not desirable. So as a trade-off between datagram packet switching and pure circuit switching, a virtual circuit switching was proposed. This found use in different technologies, ATM, frame relay, X.25, so on and so forth. So a point to note is virtual circuit switching operates over a packet switching core, by which I mean underlying this is the store and forward architecture. So the store and forward architecture supports applications that do not need any resource reservation. But if your application needs resource reservation, you can take a connection-oriented approach through this use of virtual circuit switching. So basically in virtual circuit switching, a connection much like in circuit switching is established between the source and destination before you can send packets. And while this connection is being established, you can reserve any resources that this particular application flow requires. Since you are operating on a packet switching core, the packets that you are sending to a switch need to carry some information on what to do with this particular packet. This is done through what is called a virtual circuit identifier, VCI tag. This is carried inside the header of packets. So here is what happens. Before you send any data, you need to set up a connection between the source and the destination. And at each switch between the source and the destination, this is what you're going to do. You look at what the destination address is, and based on this, you create a mapping between an incoming VCI port to outgoing VCI port. All this will become clear shortly when I cover an example. The point to note here is the later packets that come will not carry a destination address but will carry a VCI tag. As part of this connection setup itself, as at each switch, you may also reserve resources. A point to note here is that a switch for a given connection, the VCI on a port has to be unique. This uniqueness is local in scope. In other words, this should be unique only at the switch. The same VCI could potentially be used at some other switch. Note that the same cannot be said about addresses used in datagram switching. The addresses have to be unique to ensure that the forwarding path takes the right path. Whereas here, the VCIs that you are using need not be unique across switches, but they need to be unique on a given port at a particular switch. Again, this will become clear through an example. And since this VCI is local in scope, this field can be much smaller. In other words, the number of bits that you need to represent this tag is going to be much smaller than the address field used in datagram switching because this is global in scope. This has to be unique across all the hosts, whereas this needs to be unique across only the connections that are passing at a particular switch on a given port. So this example should clarify whatever was covered so far. So in this example, host A wants to send packets to host B. Before it sends these packets, it's going to establish a connection. So for that, host A will contact switch 1 and say, I want to talk with host B. Now the switch 1 is going to notice that host A packet has come on port 2, so it maintains what is called a connection table. Within this table, it is going to note that when a packet comes on port 2 corresponding to this particular connection, I will assign it a VCI of 6. And then it is going to notice that the destination is B. To reach B, it has to send it on port 1. This information it gathers, much like in datagram switching through the forwarding table. So it does have a connection table as well as a forwarding table. The forwarding table tells to reach B, you need to send it out on port 1. So this connection table, it is going to fill that information. It doesn't know which out VCI to use. This will become clear shortly. And then it is going to pass this packet to switch 2. Similarly, switch 2 will notice that this packet has come on port 3. So it will note the input port as 3 and it is going to assign 5 as the VCI corresponding to this particular connection. And through the forwarding table, it will figure that this packet has to go on port 2. Thereby, it will set the output port to 2. Out VCI, it doesn't know. And similarly, at switch 3, it will note the in port as 3 and this is something that the switch 3 is assigning, and it decides that to reach host B, it needs to send it out on port 1, so it is going to put the output port as 1. Now when this connection setup packet, which has traveled like this, has reached host B, now host B, if it decides to accept the connection, it will allocate a VCI of, in this case 3, to identify the flow from A. Now what B does is it in turn acknowledges this connection, and when it is acknowledging this connection, it will specify to switch 3 that I have assigned a VCI of 3 for this particular connection. Thereby the switch 3 is going to fill the out VCI here based on 3. In other words, this is telling that if you want, B is telling switch 3 that if you want to send me packets from host A, use an identifier 3. That is how I identify the connection from A. So that's why it is put out VCI as 3. Similarly, switch 3, because it used an in VCI of 5, it is going to tell switch 2 to use an out VCI of 5. So this gets represented here, and similarly this gets represented here. So point to note here is that the same VCI 5 is being used at the different switches. So this is local in scope and not global in scope. Now as this ACK from B propagates back to host A, all these out VCI fields are filled up as shown here. Now forwarding of packet is very straightforward. So when host A assembles a packet to host B, it is going to put a VCI of 6 and send it to switch 1. Now switch 1 is going to now consult the connection table, and within this table it is going to see that this packet has come on port 2 with VCI 6, which means I have to send it out on port 1 and with VCI 5. In fact, this is the table you should look at. So this is going to forward this particular packet, but it is going to replace this VCI 6 with VCI 5. Now when switch 2 comes, again it's going to look at the connection table. So this packet has come on port 3 with VCI 5, which means I have to send it out on port 2 with VCI 5. So then it's again going to send this packet, but it will change the VCI from this to this. In this case it turns out to be the same, but if it were different it would change it. And similarly at switch 3, when it is going to send it out to host B, it changes the VCI to 3. So if you notice, the forwarding table is not being looked at to forward the packet, only the connection table is being looked at. So why maintain two tables in virtual circuit switching? So one is through the connection table, this connection establishment itself. Based on this, you can potentially reserve the resources. That is in fact the main reason. When you get this packet on port 2 with incoming VCI, you may decide that this has certain priority and thereby let me send it ahead of any other packet. So some such rules can be applied. Another big advantage of maintaining a connection table is that the switching can be done in hardware, whereby the switching speeds can be increased significantly. Looking up at a forwarding table, again this will become clear more when we cover the IP protocol, but this can be rather tedious. So here, through maintaining this in hardware itself, you can quickly send packets very fast across the switches. So that is another advantage of virtual circuit switching. So here are the characteristics of virtual circuit switching. Basically, through this use, you can reserve resources during the setup phase, and these resources could be buffer space, the amount of space in the queue, or the link bandwidth itself. Now, before you can send the first packet in your connection, how much time do you have to wait in virtual circuit switching? Because of this connection setup, this packet has to go all the way to the destination and the ACK has to come all the way back before you can send a packet. So this can take at least one round trip time. And another thing which is nice about virtual circuit switching is it has less per packet overhead. The VCI tag is much smaller than the address tag that is being used in datagram switching. But the biggest disadvantage is if something failed, the switch failed, all the old connections need to be toned down and a new connection needs to be established. So this is not as fault tolerant as datagram switching. So that's with virtual circuit switching. Let's move on to the next, source routing.